now that you've learned a little bit about what CC does and why we do it as it pertains to the GMAT, we'd like to take some time to give you a preview as to the kind of things that you would learn in a GMAT course with CC. Now, for those of you that don't know, data sufficiency is a type of question asked on the GMAT. Now, you'll notice that there are no answer choices presented on this slide, and that's because the answer choices on a data sufficiency problem are all the same. So we'll cover exactly what all the answer choices are whenever you come into class. But for now, just know that we can use one of two charts to help us evaluate the answer choices more quickly on the basis of the fact that the answer choices are not going to change. What will change are the components of the question. So let's first cover the components of a data sufficiency question. You'll have what's called the stem, which will give you some information, and then you'll have two statements. Now the stem is called as such because it's not a complete question. The other information contained in the question are in statements 1 and 2. But the question stem will ask a question that you are required to determine whether or not you are able to answer. So you could think of it this way. There are three components to a data sufficiency problem. The question that's asked by the question stem, and then the statements 1 and 2. Now, if you remember blocks when you were a child, playing with blocks, you could build a tower by stacking blocks on top of each other. Our job is to determine whether or not statement number 1 can support an answer to the question given by the question stem by itself, or if it needs 2 to help it. Vice versa, we also need to determine whether or not 2 can hold the question stem by itself, or if it needs 1's help. Or, even if we use both blocks 1 and 2, maybe these blocks are too small to give any support to the block denoted by our question stem. So our job is to determine whether or not we can make a tower out of these three pieces, so to speak, and hold up the question stem. So as a practical approach, we'll go through an example now. If m is an integer, is m over 12 an integer? Well, is it? First of all, we need to know something about integers. What are they? Well, if we look at the number line, we have 0, -1, -2, +1, and +2. Integers are the counting numbers, all of the whole numbers, and that includes both positive and negatives. Right? Integers do not include fractions. So any numbers like 1/2 or 3/2 are not integers. So the question is asking us, given that we know m is a whole number, is m over 12 an integer? What does that mean? That means, is the number that we don't know, m, is that whole number divided by 12 going to give us another whole number? Well, how would we know the answer to that question? Well, what numbers can be divided by 12 and give us a whole number? Multiples of 12 when divided by 12, will give us a whole number. So if we have 12, 24, 36, 48, so on and so forth, there are an infinite number of multiples of 12. If I divide each of these by 12, I get 1, 2, 3, and 4. Now, the question is, why do I get 1? Why do I get 2? Why do I get 3? And why do I get 4? And obviously, if I divide 24 by 12, I get 2. That's great. But is there a more succinct way? Maybe succinct is the wrong word to use. Is there a different way to look at these numbers that can help me not only on this problem, but on other problems that deal with divisibility? Well, let's take a closer look at this 12. And let's take a closer look at something called prime versus composite. Now, what is a prime number? A prime number is a number that can be divided only by itself or 1. A composite number, on the other hand, is a number that is composed of primes. Okay. So we may have recalled something about primes from our previous educational experiences, but can we list them off the top of our head? Maybe, maybe not. So let's start with 0, 1, 2, 3, 4, 5, 6, 7. Now we know there are more numbers in the number line, but we'll just evaluate these first few terms. 0 divided by 1 is 0. Okay, so it's divisible by 1. But 0 divided by 0 is undefined. Think about it this way. How many times can 0 go into a number? It can't go into a number any time, so anything divided by 0 is undefined. 0 is not prime. 1 divided by 1 is 1, so that's divisible. But 1 or itself. As a caveat, something that I failed to mention, we need exactly 2 unique factors. So while 1 is divisible by 1 and itself being 1, it only has a singular factor, 1, and therefore by the definition of the primes, it is disqualified from being considered prime. Although it's worth noting, 0 and 1 will come up quite often in our study of the GMAT mathematics. Now let's take 2. 2 divided by 1, okay, that's good. 2 divided by 2, that's good. 2 is prime. We'll also notice that 2 is the only even prime number. But I'm getting ahead of myself. Let's look at 3. 3 divides by 1. Yep. 3 divides by 2. Nope. 3 over 2 is not a whole number. But 3 over 3 is. So 3 can only be divided by 1 and 3. 3 is prime. 4 divides by 1. Yep. And actually all of these will divide by 1. But 4 can be divided by 2. 4 is a composite number. And it's composed of 2 times 2, or these primes. 5. 5 cannot be divided by 4. 5 cannot be divided by 3. 5 cannot be divided by 2. 5 is prime. 6 can't be divided by 5, can't be divided by 4, but it can be divided by 3. So we'll notice that 6 is composite, and it's composed of 2 and 3, both primes. 7 cannot be divided by any of the lesser integers, and is therefore prime. 2, 3, 5, and 7 will come up quite often on this exam. But what you might notice is that 4 has two 2's and 6 has a 2 and a 3 in it. This is worth noting. Because every composite number has a unique prime factorization. That is, there are a unique set of primes that will generate the number 4. And there are a unique set of primes that will generate the number 6. So if we were to take the primes 2 times 2 times 3 times 5 times 7 times 5 times 3 times 2, and we were to figure out with a calculator whatever that number multiplies to, we would have a completely unique number. And there's no other way to get that number other than those primes. Now, that might seem like we're splitting hairs, but in fact it can be quite useful. Now, why is that? Well, let's take, for instance, the fraction, I don't know, 12 over 4. I take that back. Let's take the fraction 4 over 12. What is this fraction reduced to? Well, some of us might say, well, they're both divisible by 4, so that's 1/3. True. But how could we use prime factorization in a way that we might not have seen before? Well, 4 is equal to 2 times 2, right? What about 12? 12 is equal to 2 times 6, and 6 is equal to 2 times 3. So no matter how I do it, 2 times 2 times 3 is going to be 12. So 2 times 2 times 3 is equal to 12. So 4 over 12 is equal to 2 times 2 over 2 times 2 times 3. Now what happens when I have 2 over 2? Well, that just cancels to 1. What happens if I have 2 times 2 over 2? Again, cancels to 1. So what do we have on top? We have a 1. What do we have on the bottom? 1/3. Ah, now here's something we can use. So any unique prime in the bottom of a fraction, or the bottom of a division bar, which is called the denominator, by the way, will give us a fraction as our final result. It will not be a whole number. For instance, if we were to invert this, maybe it'd be better if we did 18 over 6, which we may think of 18 over 6 is equal to 3. Well, let's say you're not as good as your times table as this next person. What's the prime factorization of 18? Well, I've got a 2 and a 9, and the 9 goes to 3 times 3. What about 6? 6 goes to 2 times 3. So 18 over 6 is equal to 2 times 3 times 3 over 2 times 3. What happens to the 2's? They cancel. What happens to the 3's? They cancel. What are we left on the bottom? 1. So we have 3 over 1, or the whole number 3. So therefore, by using the prime factorization, we've proven that 18 over 6 is an integer. Specifically, that integer is 3. Now, how will this be useful in answering our question? Is m over 12 an integer? Well, if you will allow me to clean up some of our workspace here. go ahead and talk about what exactly that means. So m over 12 is an integer. That means we can't have any unique primes in the bottom. So what is 12? 12 again is 2 times 6, and 6 is 2 times 3. So what the question is really asking us is m over 2 times 2, times 3. Does this division give me a whole number? Well, when would this division give me a whole number? This division would give me a whole number when m itself has a 2, a 2, and a 3, and possibly something else in the prime factorization. So this is the real question that the GMAT is asking me. The GMAT's really asking me, is there a 2, 2, and a 3 in the prime factorization of m? Because if this is true, then that is also true. Now, at this point in time, it's worth noting that we really only need to know, can we prove that there are these three numbers inside of m, or disprove that these three numbers are inside of m. If we can disprove that these three numbers are inside of m, so that either there's only one 2 and only one 3, and not a second 2, well, then we would answer, is m over 12 an integer? Well, if we know that there's only one 2 and not two 2's, then we could say no. M over 12 is not an integer because only one 2 will cancel, and we'll be left with at least one 2 on the bottom, giving us a fraction. Okay, so that's the first step to success on the data sufficiency questions, is finding out the real question. Now that we understand what the real question is, and we've learned a little bit about prime factorization, let's take a look at our statements. And for this situation, I'm going to evaluate statement number 2 first. So as you'll learn, we need to use this chart when evaluating statement number 2 first. Okay. Statement number 2, 6m over 12 is an integer. What does that mean? That means 6 times m over 12 equals a whole number. Okay, is there something more we can do with that? Well, obviously we can turn 12 into its prime factorization, and it's probably a good idea that we turn 6 into the prime factorization as well. So this is simply 2 times 3 times m over 2 times 2 times 3, which is all equal to a whole number. Well, what happens? These 2 cancel and give us 1. This 3 cancels with that 3 and gives us 1. So what is this statement really telling us? The statement is really telling us m over 2 is a whole number. Well, what does that mean? That means this 2 is going to be canceled by something in the prime factorization of m. Or alternatively, if we want to draw a picture, m's prime factorization has a 2 and maybe something else in it. But nothing else, it has at least a 2. Because if m was just 2 and this question mark was 1, 2 over 2 would be 1, or a whole number. Right? But that's all that it proves. It just proves that we have one 2 inside of m. Is that enough information to prove that there's at least two 2's and a 3 inside of m? Now be careful. It may be tempting to say, no, that's not enough information to prove, which is technically correct. But it's not enough information to disprove it either, because we still have this question mark. See, if m were to be equal to 2, then no, there aren't a 2 and a 3 in there. But if m were to be equal to 24, which is divisible by 2, which, by the way, is 12 times 2, and since this is 12, I know that 12 is composed of 2, 2, and 3. There's a 2, 2, and a 3 inside of 12. That would mean if M was 24, then yes, M would contain 2, 2, and 3. So in this case, when we say 6m over 12 is an integer, and we're asking is m over 12 an integer, we can only say maybe. Well, we can't really prove that this is the case, but we can't disprove it either because m might contain some other primes in its prime factorization that we're not aware of, and that we can't prove because only m over 2 is a whole number. For this reason, as you learn what each of the answer choices are, we'll go ahead and cross out answer choices B and D. Now, as a side note, if you're taking the exam and you learned how to use these charts, let's say you only get to evaluate statement number 2. Well, if you've evaluated statement number 2, you've at least narrowed down your answer choices to one of 3 choices. So if you're running out of time on a problem and you need to go ahead and click an answer to move on, at least now you've increased your guessing accuracy to 33% versus 20% when you have to choose from 5. And that's the very purpose of this chart. Now, let's take a look at statement number 1. What does statement number 1 say? 7m over 12 is an integer. Well, what does that mean? That means 7 times m, and we can't break down 7 because it's already prime, over 2 times 2 times 3 for 12 is a whole number. Well, here's my question. Is the 7 going to cancel the 2? No. Is the 7 going to cancel the 3? No. 7's prime. It's not going to divide evenly by 2, 2, or 3. But we know, because the result of this entire operation is a whole number, there must be a 2, and a 3 on the top of this fraction sign. And it's not coming from the 7. So where must this 2, 2, and 3 come from? Clearly, the 2, 2, and 3 must come from the prime factorization of m. So therefore, we'll notice that this statement is sufficient to say, when we're asked the question, does m have a prime factorization of 2, 2, and 3, and maybe something else? We can clearly say, yes. Yes, it is. Yes, these numbers are contained in the prime factorization, and therefore m over 12, yes, is an integer. Again, once you've learned the answer choices, we'll be able to select answer choice A. And we'll see that statement 2 couldn't hold up the block of the question stem, but if we were to move it appropriately, pardon me, if we were to move the question stem appropriately, statement 1 will hold it up without a problem, and we can make our tower. To continue on with the analogy that we made at the beginning of the lecture. Now, not all of the data sufficiency problems will take this long to go over, but as this is likely your first experience with the conceptual learning that goes on at CC, and possibly one of the first experiences you've had with a data sufficiency problem, it's appropriate to take the time necessary to go over these actual concepts so that you are able to understand what the GMAT's really asking you so that you can better evaluate what the answers are. Now, in the beginning of the learning process, we won't focus on speed. We'll focus on learning what you need to know and what you need to do in order to respond effectively to the questions. Once you have an idea of the concepts, then we can work on your speed over time. And that's where the homework assignments will come into play. The more homework assignments that you do, the quicker your response will be on the GMAT. And as you'll learn in the classes, time is a very, very important factor for success on this exam. Well, that about wraps it up for today's lesson. Thank you for taking the time to listen to this presentation. We hope that it was very informative and gives you a better picture of what to expect from CC. Thanks. Have a great day.